Okay. So, today in the fourth lecture, we will start with the derivative of function of several variable. So, once again I have a function f defined from some subset u in Rn to Rm m and n as before greater than or equal to 1. When we talk about derivatives, unless otherwise specified, you know it happens in for function of one variable also. So, unless otherwise specified, we assume U to be an open connected set. Because there is always a problem in defining derivative at boundary, this becomes one sided. Okay. So, before defining or what should be the definition of derivative here, let us try to see or recall back what happens in function of one variable. So, recall back, suppose I have a function from an open interval a b to R, x naught is a point in a b, then we say f is differentiable at x naught. Something like this happens, that limit h goes to 0 correct, this exists and we call it f prime at x naught. So, what is the meaning of this definition? Let us put a star here. What is meaning of this definition star? Well, it is here. You have f defined here. Now, you have a point x naught and here is your f x naught. X naught plus h goes to 0, h can go to 0 from either side, negative side and positive side. So, if x naught, if you take negative, then x naught minus h here, and if you take positive, then okay, let us do it little bigger. So, this is the interval h, length of the interval h, this is x naught plus h and here is your f x naught plus h. Look at the numerator, this is precisely the difference, this. Correct. I am dividing by h, which is this length. So, you see, if I join these 2 points by a straight line, if I have this angle, this numerator, if I call this angle depending on h theta h, the theta h is this ratio, tan of theta h. And what is the idea of defining this? Oh, well, as h goes to 0, this as h goes to 0, this ratio actually gives you that this ratio goes to tan theta, which is the slope of the tangent at f x naught. This is the geometry behind this definition. If you do it from for x minus h, x naught minus h, similarly you have to approximate this side, and this will also the demands that both way it should converge to the slope of the tangent at f x naught, at x naught, sorry, slope of the tangent of f at x naught. Yes. Okay. So, simple geometric interpretation of derivative. Now, if I try to just generalize this notion directly to function of several variable, how should I think? Well, look at this ratio actually measures the difference between the value of f x naught plus h and f x naught divided by the length of the interval, correct. So, maybe our first instinct will be that, well, let us try this. I have a function from an open set U, open connected set U in Rn to Rm. So, given an x naught in A U, I should say f is, so this is a possible definition. Okay. X naught f is differentiable at x naught. Well, what I do? I look at f x naught plus h minus, so it is Rm valued, so it is a vector in Rm minus this vector f x naught, and h is increment. So, I divide by the length of the increment, and here the concept of length is norm, and then try to put limit h goes to 0. Recall that h goes to 0, h goes to 0 in, this is same as saying norm of h goes to 0, that follows from the definition of norm, right. And if this exists, then I will call it differentiable and I will denote it by f prime at x naught. Well, what is wrong? I mean, fine, we just lifted the idea from one variable to this several variable. But whatever we lift, if we go back when n equal to 1, u is an interval and m equal to 1, that is the case of single variable, this should match to our original definition of concept of notion of differentiable function for one variable. And looking at this definition, you can see that immediately there is a problem. What is the problem? So, what I am trying to do here, I have come up with the possible definition of derivative for function of several variable. Now, I see it is, if it matches with my original notion, when n equal to 1, m equal to 1 and u equal to a b and x naught is a point in a b. Well, look at this function f x r to r, the famous one, mod x, and x naught equal to 0. Let us put this definition, limit, now single variable h goes to 0, plus h minus f of 0 divided by length of h which is limit h goes to 0, by definition 0 plus h minus 0 divided by h, which is equal to 1. So, exist, that means according to my definition this f will be differentiable at 0, but all of you know it is not. It is the first example you do of a non differentiable function. That what happens here? This is mod x, graph of mod x at 0, this is like this, and as I said that differentiable existence of derivative means it gives a slope of the tangent at the point, but at this point of course you cannot do any unique tangent, there is no unique tangent exist, f is not differentiable. So, what is going wrong? So, this definition I have to discard. What went wrong? Well, if I look back, then I see the problem is that I have put the length here, and while actually derivative I do not put the length here, I just divide by h. So, what is happening? Why mod x is not differentiable? That all of you know that if I approach 0 from this side, this limit is plus 1, and if I approach 0 from this side, the limit is minus 1. So, limit does not exist at 0, therefore, f is not differentiable. So, I cannot put this mod here. So, now I reflect once again, maybe it is because that I have to approach through direction, this direction matters, positive direction or negative directions, and in real line there is only one direction, this one, and it is negative 1. So, basically 1. So, maybe while defining derivative for several variable, we should take care of a direction, that we should be able to approach for all possible direction, and what we can come up with a possible solution that, well, here is my u, I want the derivative at x naught, I should be able to approach x naught from all possible direction, and then we will see that if the limit exists. That is what I mean here, that another possible definition, okay, x naught is in u, and I take u in R n a norm 1 vector that will define a direction, right. Any norm 1 vector defines a direction. The direction is precisely given by one norm 1 vector, and I should define, I should look at f of x naught plus I should approach through this direction, then f of x naught divided by h, I cannot put sign here because I have to approach from negative as well as the positive of u, and then put h goes to 0, h is real, and if this exists, then f is differentiable. I am not saying that this is a definition, I said this is another possible definition which we, after reflection about the drawbacks of the previous definition, we may come up with this definition. Okay, not bad. This will take care for n equal to 1, m equal to 1, this takes care of f x equal to mod x. It is not differentiable at 0. If I put this definition, so that is the modification I have done, not bad. And I want for every possible So, I should write for every possible u, this thing happens. Okay. But let me put another example here. Let us say f from very simple one R2 to R. Let me recall f of x y equal to, let us say, x y square x square plus y power 4. I think this will work, where x not equal to 0 and 0 if x equal to 0. You can just see that this function, according to this definition, if x not equal to 0, y not equal to 0, at 0 0 except 0 0, everywhere it will satisfy this definition, everything is very nice. But let us check it, check at x naught y naught equal to 0 0. So, I put this definition, limit h going to 0 f of 0 0 plus, so I fix a u with norm of u1 u2 equal to 1 plus u1, sorry, let me write it more clearly, f of 0 plus u minus f at 0, 0 means the vector 0 0 divided by h, that will give me what by definition u1 u2 square, oh sorry, there is a h, right, that will give me what h cube u1 u2 square divided by h1 square u1 square plus h2 4, sorry, h square h4 u power 4, correct, everything divided by h. Check that is correct. And now if I put, so I have a limit h going to 0, if I put limit h going to 0, you can calculate this will turn out to be u1 by, so u1 square by u2, no sorry, u2 square by u1 if u1 not equal to 0 and 0 otherwise. This is the limit. Very good, limit exists at 0 0. So, according to my this definition, f is differentiable at 0 0, but you can easily check f is not continuous at 0 0. Why? You just approach through the line y equal to root x, you will see that at 0 it does not match. So, you check that f is not continuous at 0 0. So, then I have a very serious problem, because I do not, I want differentiable function to be at least continuous. If I am able to do tangent to a graph or tangent to a point, tangent at a point to the graph, and the function is not continuous at all, there is a jump, then what do you mean by a tangent? So, this defies our geometry. So, this derivative again I have to discard, but possibly we will not discard it, as it is not too bad. So, we will discard it with a little bit reservation and we will come back to it. We will call it later on directional derivative and it will be useful for us, but for time being this cannot be the definition of differentiable function of several variable, because if it is a differentiable function, at least we want continuous, and this function is not continuous, but turns out to be differentiable according to this definition. So, I have to look back my star little bit carefully. What was star for f a b to r? Limit h going to 0, f of x naught plus h minus f of x naught divided by h exists, and we call it equal to f prime x naught. We observe what is happening here is actually that this f of x naught plus h minus f of x naught, there is an increment that is equal to, from this I can write f prime of x naught into h plus h into some error term, where goes to 0 as h goes to 0. So, that means to say f prime x naught into h approximate this increment f of x naught minus f of x naught, correct, in this sense. And second, this approximation is linear. What does it mean? That h going to f prime x naught into h, this is a linear function from R to R, because on R to R any linear function, I am not writing it, listen to me carefully, any linear function from R to R that is given by alpha in R such that L of h equal to alpha h by multiplication. And the last thing, property 1 and 2 I written on that board, determine f prime x naught uniquely. I will leave it as an assignment exercise, and what it mean by this is, if f x naught plus h minus f of x naught equal to some alpha h plus h into e x naught h, e x naught 1 h, and also equal to beta h plus h into some e x naught 2 h, where e 1 x naught h and e 2 x naught h both goes to 0, as h goes to 0, then alpha equal to beta. So, if f prime x naught is uniquely determined based to property, this I put an exercise, and the next class we will start from here and come up with the right definition of differentiability. Thank you.